Good morning, Chem class. Let us start with some words of wisdom from St. Augustine. Faith is to believe what you do not see. The reward of this faith is to see what you believe. Today we're going to see that one of the very practical applications of the ideal gas law is that it allows us to find molar mass, that is molecular weight. So a reminder that molar mass is an intensive property. An intensive property is one where the property does not change with the size of the sample. And so it is very helpful in identifying unknowns. A reminder that the ideal gas law can only be used to find the molecular weight of unknown gases. It would not apply to liquids or solids. So the ideal gas law can be used to calculate the molar mass if a chemist simply, when he was running an experiment, would measure all the conditions of the gas, so the pressure, the volume, the temperature, and one additional piece of information, the mass of the sample in question. Then he would be able to solve for the number of moles of gas because you would have the pressure, volume, and temperature. And now remember, molecular weight is simply grams per mole. So now you would have a ratio of the mass you use, the extra piece of information that you measured, per the moles that you calculated using the ideal gas law. And now, voila, you would have the molar mass of this gas. So let's look at an example. We're being asked to find the molar mass of a gas if 300 centimeters cubed has a mass of 0.855 grams at STP conditions. So we know we're going to need PV equals nRT, and we're going to start by plugging in our value for R, the 0.0821 liter atmosphere over Kelvin mole. We want to begin by plugging in the R value because that makes us well aware of all the other units that we need for the specific variables. Recall that STP conditions means the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. So we can easily plug in our 1 atmosphere for pressure, since that is what our R value is telling us we need for the particular unit. Volume. Our volume is 300 centimeters cubed. A reminder that a centimeter cubed is the same thing as a milliliter. So I'm going to write milliliters, and we want liters because of our R. So 1,000 milliliters per liter, and we will get 0.34 sig digs, the way that is written, liters. Now we will plug that in for our V. We're solving for N. T must be in Kelvin. Standard temperature is 0, so we add 273 to that, and we will have a temperature of 273 Kelvin. Now we're simply left to solve. Units cancel. And we are left with N will equal 0.0134 moles. But we're looking for molar mass. Remember, molar mass is the number of grams per mole. I just solved for the number of moles that I have in this sample, so I have 0.0134 moles in my denominator, and I return to the original problem and find that the mass for that sample was 0.855 grams. I plug this in the calculator to 3 significant digits, and I get 63.9 grams per mole. the molar mass. Let's look at a second example. A liquid is vaporized at 100 degrees C and 755 millimeters of mercury. The volume is 0.627 grams of the vapor is 261 milliliters. What's the molecular weight? Notice here that it started as a liquid, but they're talking about the vapor because we can only use PV equals nRT if we are talking about a gas. So let's start by writing PV equals nRT and fill in our R value to remind us of the appropriate units. Now I'd like you to pause the video and try and complete the problem on your own and then come back. So we would have to change our pressure to atmospheres. We would have to change our volume to liters. We're solving for N. We have our value of R, and we had to change our temperature to Kelvin. Now it's simply simplifying the algebra. And oops, I have a missed copy. It should be 0.993 atmospheres. Plugging through, we finally get N equals 0.00846 moles. Now to answer the question, the number of grams per mole, we return to the original problem and see that we were given the mass, 0.627 grams for this sample size, and we just calculated the moles of this sample size, 0.00846 moles. We plug that in our calculator. We're going to round to 3 significant digits when we go back and look at the original data. Nothing is less than 3. And putting that in my calculator, I get 74.1 grams per mole. I hope you got that too. I personally solve molar mass problems for gases using the approach that we just went through, because all that we're using is PV equals nRT and then taking the mass, dividing by that number of moles. However, you will find that many textbooks give you an alternate approach, and I'm letting you pick this. It simply means you need to know another equation, and I like knowing or remembering as few as possible. So if we start with PV equals nRT, and remember that N is simply mass divided by molar mass. That's how you calculate how many moles in any problem that we've done. So now I'm going to make an algebraic substitution for N. PV equals mass divided by molar mass times RT, where little m equals mass, capital M equals molar mass. Simply going to rearrange and solve for capital M, the molar mass. And we would have molar mass equals mass times R times T over PV. Here mass would have to be in grams always. And if we're going to use the R of 0.0821, it again is limiting our pressure, volume, and temperature units. Let's go back and solve this second problem using this alternate method. Again, it's very, very straightforward. We're just plugging things in an equation. The only thing is you have yet another equation to remember if you're going to use this approach. I'm simply going to copy the pressure, volume, and temperature from our last work through example. We already did those conversions. We plug in our mass, 0.627 grams, our R with the appropriate units, temperature, our pressure, and volume. Cancel all our units, atmospheres upstairs and downstairs, Kelvin upstairs and downstairs, and liters upstairs and downstairs. That leaves us with units of grams per mole. Notice that is in the denominator, which is what we would expect if we are solving for molar mass. So now we simply need to plug all these numbers in our calculator. And once again, if I go through that and round to 3 significant digits, I would get 74.1 grams per mole. Right, so you saw 2 different methods for finding molecular weight of a gas using the ideal gas law. Your choice on which you want to use, and you'll have some practice problems to show that you've mastered this skill.